Okay, let's begin to do the review. And I will solve some hard problems, okay, for you guys for the review. Okay, I'll pick some typical and also difficult problems from each section to solve for you guys. So this is review for chapter 6. Right? And let's first begin with one problem in the section 1. Let's look at the page 516. We'll look at problem 23. Okay, in this 23, we know the value of the tangent alpha, and we also know the position of alpha. Alpha is in the quadrant 1. And then we need to find the exact value at alpha for the remaining 5 trigonometric functions. Okay, so let me list these two knowns in the whiteboard. So we have the tangent alpha equal to 1/2. And we also know alpha is in the quadrant 1. So now we need to find the function values at alpha for the other 5 remaining trigonometric functions. So that means we need to find the cosine alpha, sine alpha, okay, cotangent, secant, and cosecant. And let's begin with the cosine alpha, because we know the relationship between the tangent and the secant, right? So it's easy to find the secant alpha. We have the Pythagorean identity, tangent square alpha plus 1 equal to secant square alpha. Okay? So now from this identity, we can immediately find the secant alpha. Actually, you have the secant alpha. Since alpha is in the quadrant 1, so secant alpha is positive, right? So secant alpha is equal to the square root of the tangent square alpha plus 1. Now you plug in 1/2. For this tangent alpha, you have the square of 1/2 and plus 1. Then you take the square root. Okay, so this is the 1/4 plus 1. You have the 5/4, right? And then you get root of 5/2. So this is secant alpha. Then after we find the secant alpha, we can immediately get the cosine alpha. So cosine alpha, which is the reciprocal of secant alpha. So you just invert this fraction, then you have the 2 over the root of 5. And then you rationalize by multiplying both the numerator and denominator by root of 5. Then you have the 2 times root of 5/5. So now, after we find the cosine alpha, then we can use one of the Pythagorean identity, that is a fundamental identity, to find the sine alpha. So sine alpha, and since alpha is in the quadrant 1, so sine alpha is also positive. So sine alpha is equal to the square root of 1 minus cosine square alpha. And then let's plug in the values. Okay, the value for the cosine alpha into this expression. We have 1 minus the square of 2 times root of 5/5. And then this guy is equal to 1 minus, okay, you compute this, you got the 4/5. So this is equal to square root of 1/5. And this is equal to 1 over square root of 5 you rationalize, then you get root of 5 over 5. So now, from here, we can immediately get the cosecant alpha. Let's move to the next page. So cosecant alpha, which is equal to the reciprocal of sine alpha. So sine alpha is equal to 1 over root of 5. So cosecant, this is equal to 1 over root of 5. So it's just equal to root of 5. And then the last one, cotangent. Actually, cotangent is a simplest, right? It's equal to 1 over the tangent alpha. And the tangent alpha is equal to 1/2. So this cotangent is equal to 2. And then done. I know many of you guys have trouble with this type of the problems, right? So now let me solve one more problem of this type. And let's look at the 33. So find an equivalent algebraic expression for this expression, okay, for this composition. Tangent of the arc sine of x. So this is a page 516. And let's look at the problem 33. So we need to simplify this tangent of the arc sine x. So first, let theta be this angle, okay, be this arc sine x. Then, by the range of the arc sine function, we know theta must be between the negative half pi and half pi, right? So first, we have the theta greater than or equal to negative half pi and less than or equal to half pi. And also, by the definition, sine theta is equal to x. Right, because theta is angle whose sine is equal to x. So now, let's rewrite this arrangement expression. Tangent of arc sine x. So let's replace this by theta. We have the tangent theta. Right now, we know the sine theta is equal to x. And we need to rewrite tangent theta in terms of the sine theta, so that we can express this composition as a function of x. And we can start with the identity from the definition. We know sine theta is equal, or tangent theta is equal to sine theta over cosine theta, right? And cosine theta, by the fundamental identity, this is equal to plus minus square root of 1 minus the sine square theta. So now we can replace sine theta by x. Then we get a plus minus x over the square root of 1 minus x squared. Now the next step is to determine the sign of this expression. And let's first notice this result. You know, if you take the x value of the both sides, you have the x value of this tangent of arc sine x is equal to the x value of this expression, right? We can just get rid of this plus minus sign. And we know the denominator, this is a positive square root of the 1 minus x squared. It's always positive. So we can take this out. Then actually it's just equal to the x value of x divided by the square root of 1 minus x squared. So now, we need to use the sine of x to determine the sine of the tangent of arc sine x. Okay, because they have the these two expressions, they have the same sign, same absolute value, right? So then in the following, we just need to determine the sine. And let's look at the case 1. Let me move to the next page.